Welcome everyone, I'm back. Previously, I tried building a 3x3 redstone door from scratch with no tutorials, no wikis, and no external information. Then, I took apart one of the world's smallest and most optimized 3x3 doors as well. But now, it's time to take on a new challenge, something a little more personal. I'm gonna build a computer in Minecraft from scratch again with no tutorials, no wikis, and absolutely no help. That may seem like quite the goal, but rest assured, I think I'll actually fare better with something like this than a 4x4 door. I'm serious, as some of you may know, I study computer science, so I've got a bit of an idea of how I could go about making this happen, and I'm taking you guys along for the journey. Hello everyone, my name is Aaron, or Flashes, and I make gaming YouTube videos on some of my favorite games. I try to figure stuff out logically, like in Minecraft, or do analysis on lore and economics in Warframe. And if you're into it, make sure to subscribe. Oh yeah, speaking of subscribing, we hit 3,000 subscribers, and this is... Hold on, wait. This is me from the future. Ooh! When I was writing the script, we were on 3K, and I made this little video for it as well. But all of a sudden, there are 4,000 of you guys. Thank you so much. I'll make sure to make content that you guys will enjoy. Now, without further ado, let's begin. The first thing we need to understand is that a computer is extremely complicated. I may study computing, but even with the amount of knowledge I have, I don't have the first clue about graphics or file storage and such. And that's pretty bad, considering that for this challenge, I'm not allowed any external information. What I do know how to make, however, is a CPU, so that's what I'm going to build in this video. But even that is quite the task. I mean, it's essentially the brain of the computer, so in reality, what I'm going to make in this video is simply a basic ALU, which will serve as a foundation as I build the rest of the computer around it. Okay, let's forget about acronyms like CPU or ALU for now, and boot up the game. Alright, I'm back. I'm in a new redstone world dedicated to making this computer, and I think I'll start by making some basic logic gates. Last night, when I was in bed, I did think up some ideas for an AND gate. Like, I couldn't sleep, so I was just thinking about that. And so I want to see if the idea, or what I remember from what I thought about, is actually going to work in Minecraft. So let's just start doing that. Okay, logic gates, AND gates, what am I talking about here? Well, essentially, when you look at what a computer is doing right down at its fundamentals, it's performing logic between inputs, and a logic gate is just a fancy way of describing a mechanism that does that logic. For example, the AND gate that I'm building on screen right now. What this does is it checks if both of the inputs are turned on, and if they are, then the output will be powered. Yeah, that's it. And while that may seem pretty basic right now, we can actually use these simple gates to do maths, and that allows computers to run games or render graphics and stuff. So what's happening here is this left input is connected directly to the output, but this right input goes into this piston and moves a block in and out of the path of this first input, right? This block acts as a switch where if the right input is turned on, then the left input's power is able to go through the block and to the output. But if, say, the right input was turned off, then this piston would retract and the left input's redstone would have this gap. Which won't let the power get through. So let's see if this works. So right now both of the inputs are turned off and our output is also off, which is good. If that wasn't the case, I would be a little worried. Now let's try just the left input being on. And as we can see, the power is interrupted here, so it doesn't work if only one of them is on. How about only the right one? Cool, but the power itself doesn't actually go through the block because it's not on. And now finally, let's see if it works when both of them are on. There we go. So we've successfully made an AND gate. Okay, I think we should make an OR gate next. An OR gate works in much the same way, but this time the output should be turned on when at least one of the inputs is turned on. By the way, when I say turned on, I don't mean that these inputs are aroused or something perverted like that. So how about instead we say true and false, and we'll represent true and false by using a 1 and 0 respectively. So a good way we can visualize what a logic gate should do is by using a truth table. So we have our inputs and every possible unique combination of them are written down. We can then write in our output column which combinations should be turned on. So for the OR gate, the output should be true as long as one of the inputs are true. In the first row, neither input is true, so the output should be false, but in all three of the other rows, they all have at least one true input, so the output will be true for all of them. Alright, here's my OR gate, and let me explain my thinking. Basically, what I did was a two-step process. Firstly, I created a gate that would output true whenever both of the inputs were false. Basically just an AND gate, but instead of checking if both of the inputs are true, it checks if both of the inputs are false. And I did this by using these blocks with redstone torches, which will reverse whatever the inputs were. Then I went to the output and I reversed it with a redstone torch again. And now this new gate outputs a true for everything except for when both inputs are false. In other words, the same as an OR gate. And we can test this, right? So when it's false, false, we have false, right? But when there's a true over here, this guy's true. When there's only one true over here, that guy's true. And when they're both on, that guy's still on. So yeah, this is a working OR gate. Let me show you something real quick. This thing you see on the screen is a CPU. Well, kinda. This is the logic behind the CPU, and I made this design and diagram back in my first year of uni. Now, don't get turned off if this looks confusing, because it looks confusing to me as well, and I made it. Bruh. Looking at it like this makes it seem overwhelming, but if we take things slow, one step at a time, we'll get there eventually. See this rectangle at the top right? This is the AOU. Its whole job is to do maths and logic. It's basically just a calculator, but the work that it does is essential for anything else to run. This is what we're going to try to make today, and if we click into the circuit diagram for the AOU, we can see that it was hiding a whole bunch of BS. I don't remember how any of this works, I'll be completely honest, and I'm not going to try to decode my past work as that could be considered cheating the challenge. But I think for the video's sake, it's a good idea for you guys to see this. Oh yeah, and you know how we made those logic gates in Minecraft? Well, these shapes you see on the screen are logic gates too. For example, this bullet looking one is precisely an AND gate. It takes two inputs, and if they're both true, then it outputs a true as well. In this video, we're going to make a super basic AOU as a bit of a proof of concept that I should be able to make the whole computer eventually. Our AOU needs to be capable of doing two things. It has to be able to do addition, and it has to be able to do subtraction. It's basically just a calculator for now. And if you're wondering why we're not doing multiplication and division in this episode, it's because we would require some extra things external to just the AOU for that. So we'll get to those two operations in the next video. To do addition and subtraction, we need something called an adder. Yeah, I know, very creative, but there are a couple of types of adder. I think we should start with what's called the half adder. But before we can go back to Minecraft, I need to figure out what this half adder is supposed to actually do, because I'll be honest, I don't remember. What I do know is that the half adder's whole job is to take two inputs and add them together. But how can you add inputs together? That doesn't exactly make sense. To understand this, we gotta take a step back and learn a new language. I mean, kinda. See, we humans do maths using numbers, right? And most of us, French people, use something called decimal when we count. Decimal, or base 10, just means the counting system with 10 available digits. Okay, let me give a proper explanation. With decimal, we have 10 digits at our disposal. These are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And with these numbers, we can count. But what about the number 10? We don't have a specific symbol to represent this number. So what can we do? Well, pretend that all numbers have a 0 before them, an invisible 0. So when we're counting up to 9, we would have 0, 0, 0, 1, 0, 2, all the way up to 0, 9. But since 9 is our largest digit, we gotta reset the counter back to 0. And at the same time, denote that we've already counted up to 9 once. So we upgrade the 0 on the left into a 1, and then start counting in the rightmost digit up to 9 again. This is how we're able to count further than the amount of symbols we have for numbers, and this is commonly known as place value. Like you've got your ones, your tens, your hundreds, thousands, and so on. And I'm sure most of you guys are pretty comfortable with this already, but what many of you may not know about is something called binary or base 2. So if base 10 had 10 digits available, how many do you think base 2 has? Yeah, that's right. It only has 2 digits, which are 0 and 1. Recognize them? We used 1 and 0 to represent true and false before. Anyways, to count in binary, we do the same thing. We start at 0 and count up to the highest digit we have available, which is 1. Now, since we don't have a digit to represent the number 2, we reset back to 0 and denote that we've already counted up once. And then repeat. These digits that can either be 0 or 1 are called bits, by the way. I'll be referring to them as such from now on. But you may be thinking, how are we supposed to count anything with only 2 digits? That's going to be so tedious, and the length of our numbers are going to be super long. And you'd be right. It is tedious, and the numbers do get super long, but that's just from a human perspective. For computers, this is the most intuitive way to count. If we only have two digits, or rather two states, 0 and 1, then a computer only has to worry about whether a digit is true or false. And in the real world with electricity, these two states are just two different levels of voltage in a transistor. Or in other words, whether a signal is turned on or turned off. Pretty similar to Minecraft. So using binary, we can represent numbers that a computer can understand, and then the computer can take these binary numbers and do maths on them. But how? Here, have a look at this. How would we add the numbers 144 and something like 67, okay? And this is just talking about decimal. How would we add these? Well, we can use the addition algorithm, right? Which is just put these two numbers above and below each other. We'll start with 144, and we'll say we're going to add 67, right? And any gaps that we have, we can just put a 0 in there. And then we draw a line, and we start adding these two numbers per digit, right? So we start at this rightmost digit, then we move to the middle one, and then we move to the left one, okay? So let's start at the rightmost digit. We got 4 plus 7, which is 11, right? 4 plus 7 equals 11, okay? But we can't just put 11 in this position over here, because we only have space for one digit. So we're going to take this right number of our answer, and we're going to put that here, and then we're going to say this left number is going to be a carry to the next digit that we calculate. So we're just going to move on to the one to the left, which is 4 plus 6, which is going to be 10, but we remember we have this carry bit of 1, so we add that back onto the answer. So it's going to be 4 plus 6 plus 1, which is going to be 11 again, right? And it's going to be the same thing. We're going to put the right digit of 11 in this position here, and we're going to put the left digit as a carry bit over here for the next calculation. On the very left digit of 144 plus 67, we're going to have 1 plus 0 plus 1 because of the carry bit. So we're going to end up with 2. And our final answer becomes 211, right? And with binary, it's the exact same thing. Like, it's literally the exact same thing. So here, let's do an example. How about something like 89 plus 59? Well, first of all, let's figure out how to make these numbers in binary. So we got 89 and 59. So let's do 89 plus 59. So it's the exact same thing. We're going to put these above and below each other. And let's do it. Let's start at the very right, and we're going to add each of these digits one by one. So at the very start, we got 1 plus 1, which is 2, right? But the thing is, in binary, there is no digit for 2. 2 is represented by 2 digits. 1, 0, right? This is how you represent the number 2 right here in binary. So how can we write that? Well, it's the same thing as before. We're going to take this right digit of this 2-digit number, and we're going to put that in the answer position. And then we're going to take this left digit and put it as a carry bit over here to add with the next digit, since we couldn't add it with this one. So then we go to the next one. We got 0 plus 1 from the carry bit. So we end up with 2 again, and it's the same thing. We add a 0 in the answer, and we say we have a carry bit. Then we got 0 plus 0 plus 1, and we can actually represent that in binary, which is just a 1, and we don't even have a carry bit. Moving on, we got 1 plus 1 again, which is going to be 0, with a carry bit over here. And now we run into an interesting situation where we have 1 plus 1 and a carry bit. So we end up with 1 plus 1 plus 1, right? 1 plus 1 plus 1. What does that equal? Well, it equals 3 in decimal, but how do we represent that in binary? 3 in binary is 1, 1, okay? Not 11, but 1, 1. And we're going to do the same thing. We're going to take this right digit, put it in our answer, and then we are going to take this left digit and say that it's a carry. So our final answer becomes 100100100. And what number is this? Well, let's figure that out. We got 128 plus, that's a 16, plus a 4. So what do we have? We got 128 plus 20, which is 148. Now let's look at our question. 89 plus 59, 130 plus 18, 148. Yep. So this is the correct answer. And this is it's the exact same thing that the computer does, actually. So the computer uses this exact same algorithm. It starts at the very right, keeps in mind carries, and it just keeps adding and goes to the left. Okay, so now we know how to do binary addition. But what does that have to do with the half adder? Well, remember how for our algorithm we were adding the numbers column by column? Our half adder just needs to be capable of doing one column's worth of calculation. But how are we supposed to make that in Minecraft? Ah, snap, we gotta go back to the pen and paper. What I need to do is I need to figure out what a half adder actually does, okay?
because I don't remember what it does. I just know that it adds two digits together, okay? But what does it actually do and how does it work? So we're gonna figure this out using a truth table. So let's draw up a truth table for the half adder, right? So let's say we have input 1 or A, and we have input B or input 2 or B, and then let's also say we have our output. So we'll just say out, okay? And let's make this table. And let's write down every single different unique possible combination of zeros and ones for the two inputs. So let's say 0, 0, 1, 1, 0, 1, 0, 1. Okay. Now, what our half adder to do is essentially just an addition between one of these digits, right? Between these two numbers. So if we had a 0 plus a 0, what would we have? Well, we would have a 0. If we had a 0 plus a 1, what would we have? We would have a 1, right? If we had 1 plus 0, that would also be just 1. But if we had 1 plus 1, what would that be? Well, it would be 0. But if you remember, when we were doing binary addition, when we did have 1 plus 1, it actually equals 1, 0. It's a two-digit number. What happens to that left digit of 1, right? Well, currently our truth table doesn't really feature that, so we're going to actually have to add another column called carry, okay? Remember the carries we were using? So this is for our carry, and for all of the other rows, there was no carry, but when we have 1 plus 1, we end up with 1, 0. So our output would be 0, which is what goes into the answer, but then we have a carry bit of 1. Okay, so that is our truth table right there. Using this, we can figure out how we're going to actually make this thing. So we're going to do something called disjunctive normal form, okay? Let me write that down. And basically all this is we're going to look at the output and see every single time the output is true, and we're going to write down what specific combination we use to get that answer, right? So for example, the second row, the output is true. So we're going to say that, okay, so let's write down that we're talking about the output, first of all. And let's say that, okay, not A, so like A being false, which we're going to write as not A, or an A with a bar on top of it, that works. Or you could do a squiggly with an A, but this is easy to write. And B, we want B to be true, so not A and B. And we can just write that by just writing it next to it. Now, what's the other option? In row 3, the output is true as well. So we're going to OR this, which you can write with a plus. We're going to OR that with this other combination of A and not B. So A and not B, okay? Now this thing here specifically, this is actually called something in specific. This is an identity for the XOR gate, XOR, okay? So we can just simplify this directly because it's just an identity. I mean, we can do it using another truth table to figure that out, but it's fine, okay? This is what it's called. This is called an XOR gate. So A XOR B is what this becomes. So this gate, we're going to make this in Minecraft. Now let's also do something for the carry. If we look at this carry, we don't even have to do any like disjunctive normal form for this one. We can just have a look at it. We can see that the carry is only true when both of our inputs are also both true. That is literally just the definition of an AND gate, right? So for the carry, all we need is AB. Okay? So for our half adder, what we need to create in Minecraft is an A XOR B for the output and an AB or an A and B for the carry output.
An XOR gate outputs a true only when there is exactly one true among the inputs. So it's kind of like an OR gate, but if both of the inputs are true, the XOR gate doesn't like that and outputs a false, unlike the OR gate. So I noticed this striking similarity and decided that I would basically just have an OR gate and then cancel out the case where both inputs are true. Alright, so for this XOR gate, I've just made an OR gate, but then I have this AND gate over here, which checks if both of the inputs are true. And if they are both true, this AND gate is going to end up powering this block with the redstone torch and turn it off. And thus ultimately the output of this XOR gate will be false for that case. Cool, so that's our XOR gate and it works as intended. So for our half adder, we saw that we actually only need this XOR gate to calculate the sum of our two inputs. So let's add that in. Like so. Now for a half adder, we also need to calculate the carry bit, right? And we learned that to do this, we just need to use an AND gate. So since we already had this AND gate in the XOR part, I've just routed a second path out of that, and that's going to be our carry output. Okay, let's test if this thing works. So 1 plus 1. It didn't work? Ah, that's why. That's why, because I forgot to hook this guy up. And let's say we have 1 plus 1. Our sum is going to be 0, but we're going to have a carry bit. So essentially this is saying that our answer is 1, 0. But obviously we can't represent that with only 1 bit, so we're going to have a carry bit instead. Cool, so our half adder works. Perfect. We just did addition in Minecraft. That's crazy. But at the same time, we can only do 1-digit calculations like this. Like, the maximum sum we can create is literally 2, technically. So how can we upgrade this half adder to be able to do calculations on bigger numbers? Well, remember how we have this carry output in our half adder. What if we could plug this carry output into another half adder? If we were able to do that, we could do addition over and over. But unfortunately, this half adder can't get chained with more adders, and it's pretty obvious why. It doesn't have a carry input. So we need to make something called a full adder. The main difference is that a full adder actually has 3 inputs. It takes the 2 inputs from the numbers being added together, but it also takes in the carry output of the previous full adder, and we call that the carry input. Okay, back to the drawing board.
Okay, remember the algorithm for binary addition that I showed you guys, right? When we did 89 plus 59, right? What our half adder does is it only adds 1 digit and then it can't go any further, right? But what a full adder does is it has the capability of doing an addition with multiple digits, okay? So, for example, 89 and 59, we represent those with 8-bit numbers, where there's 8 bits to represent these numbers, right? And what a full adder or a chain of full adders can do is it can add all of these ones in succession, okay? It can actually do the algorithm, which the half adder can't do, right? The half adder can only do one column, and then it gets stuck there, right? Let's figure out how we can make a full adder using the same method we did for figuring out the half adder. Okay, firstly, let's draw up a truth table. So we're gonna have our first input, which we'll call A, and then our second input, which we'll call B. But then here's the weird thing: a full adder is gonna have a third input, right? And what is this input gonna be called? It's gonna be called CIN. Have a guess at what that means. It stands for carry input, okay? So remember how our half adder had a carry output or a carry bit? Well, we couldn't actually do anything with that carry bit, right? But what a full adder does is it allows a carry bit from another full adder to get fed into this full adder, which allows the chain of full adders to do calculations on multi-bit numbers, right? So these are our 3 inputs. Now, what's our outputs going to be? Well, first of all, we're going to have our sum output, so let's just call it S. And we're also going to need a carry output, right, for the next full adder. So let's call that one C out. So now let's write down every single unique combination of these inputs with zeros and ones. Now, we're just going to do this in our heads, but we're going to do the exact same calculation we were doing for this binary addition, right? The same algorithm, but we're just going to do it in our heads. So when we have 0 plus 0 and we don't have a carry input, right? We don't have a carry bit to worry about. What's our sum going to be? Well, it's just going to be 0. And we don't have a carry input and our number is only 1 digit, so we're not going to have a carry output either. That's also going to be 0. Next, when we have 0 plus 0, but we do have a carry input, well, our sum is going to be 1, and this is just a 1 digit, so there's not going to be a carry output this time either. And we're going to have 0 plus 1, but then we do have a carry input, and technically this is just 1 plus 1. 1 plus 1 is 1, 0 in binary, which is 2 digits. So we're going to put the right digit, which is 0, in here in the sum column, and we're going to say that we have a carry bit as well in our carry output. And finally, the weird one, 1 plus 1 plus 1, which equals 3, which is represented by 1, 1 in binary. So we're going to have a 1 as the sum, and we're going to have a 1 as the carry output. For the sum, so let's write down sum, we're going to put this into disjunctive normal form. Now, last time when we put our truth table into disjunctive normal form, we just ended up with an identity that we could just simplify directly, right? But this time, we don't have anything. This is a lot more complicated, right? We don't have anything that's like really jumping out at us. So what can we do here? Well, what we're going to do is we're going to factor. From these two, the first two terms here, we have the not A, that's common, right? And in the second two terms, we have an a that's common. So let's factor those two out. Now, do you notice anything that's jumping out at you? Well, these things in the brackets are actually XOR identities. Anyways, after that, do you notice anything now? Well, this is another XOR identity. A XOR B XOR Cn. And this bracket is, this whole XOR is just associative, so this bracket doesn't matter, but I'm just trying to be correct, and that's technically more correct here in this example. Anyways, so that is the most simplified version for our sum that we can get. Let's do the same thing for our C out, okay? Okay, so I've put them into disjunctive normal form here, right? And let's see if we can simplify this in any way. Well, what I see straight away is for these first two terms, we have Cn in common, right? And you can already see the XOR identity right there, but we'll come back to that. Plus, over here, what's common here? Well, AB is common here, so let's factor that out. To the next line, we're gonna have an XOR identity right here, so we're gonna have Cn ANDed with A XOR B. And over here, we're gonna have AB, and then this thing inside these brackets here, this is actually a tautology. So this actually simplifies to just one, because if you have something and not something, right, and you're saying or, that's every single possibility. So that's, you know, it's just one over here. So we're gonna have AB times, well, ANDed with one, which is just gonna be AB. So this is as simple as we're gonna take it for now, because this is as simple as we need it to be, in my opinion. We can simplify this further, but I think this is fine because this uses a lot of the stuff that we already have access to in our half adder, right? We already have an A XOR B, we already have an AB, and you know, Cn is just coming in later on. So we're gonna say that this is the version that we're gonna be using for our carry output. So now that we've done all the maths, which I'm sure a lot of you guys did not enjoy this segment of the video, we can finally go back to the game and actually build this stuff in Minecraft.
Let's focus on the sum first. We got A XOR B XOR Cn. Since XOR is an associative operation, let's do A XOR B first and then feed whatever the output of that is into another XOR with Cn. Okay, A XOR B is the exact same as what we've been doing before, it's just the XOR gate. Now let's take that output and put it into another XOR gate with our carry input. Okay, that's literally it for the sum. Let's go to the carry output now. Firstly, let's take this A XOR B output, since we need it, and then AND gate it with the carry input. Now let's OR gate that with the output from the AND gate between the first two initial inputs. And there we go. That takes care of our carry output. What about 1 plus 1? Uh-oh. 1 plus 1. 0 with a carry output. Okay, now 0 plus 0, but we have a carry input, is 1 with no carry output. Cool. How about 1 plus 0 with a carry input? That's effectively just 1 plus 1, so we get 0 with 1 carry output. That's correct. And we'll do it the opposite way as well, just to see. Yep. And what about 1 plus 1 with a carry input? So it's effectively 1 plus 1 plus 1. Yo! It gives us 1, 1, which is 3 in binary. And that works, yeah. So our sum is 1 and our carry output is 1 as well. So our full adder works. Cool. It's finally time to do a big calculation. But before I do that, I wanted to beautify this thing. I want to turn this huge mess into a compact and modular unit that I can copy and paste over and over. While I build that, I want to quickly ask you guys if you're liking this style of video. I mean, if you've made it to this point, then it's probably indicative that you have enjoyed it, so saying this now might cause some survivor bias, but let me know. I've decided to get pretty technical for this one and take a more educational approach where I explain the fundamentals, but I'm sure a lot of you guys don't really care about the computing side and just want to see a noob making a computer in Minecraft. But yeah, let me know in the comments. Okay, now I had this super compact unit. Well, I tried to make it compact anyways. I'm sure there are better ways to do this, but the fact that it's neatly in a 16 by 16 chunk is good enough for me. Now let's link 8 of these full adders together, making sure that the carry outputs connect with the carry inputs of the next ones. I started building this little input room where we would be selecting our numbers to do calculations on. I also made this nice big display so we could see the answers. I was so close to being finished, but then this crushing weight befell me. I realized I needed to manually connect the input room and display to the AOU. Guys, why was this so crushing? Just repeatedly building these redstone cables was genuinely mentally taxing. Like, surely there's a better way to connect everything. This deadass took me like an hour. Alright, so I finally, made all these cables. And I was thinking, oh my god, I'm almost done. And then I just realized I have to put redstone dust on all of these orange blocks. I haven't done that yet. This is taking so long. I can't take it anymore. This is actually mind-numbing, bro. Look at how many blocks I have to place redstone on, dude. It's over. It's so over. Okay. I did it. I went through every single one of these blocks, and I placed the redstone, and I made sure the repeaters made all of the redstone signals active. And it's finally time for us to actually check it out. But before we do so, I will quickly go over what I did here. So since these inputs, they're right next to each other, if I just put redstone dust next to each other, they start connecting. So what I did was I moved these guys down, and then and I alternated between this pattern, right? The top one, there's a what are these called? There's an observer that goes into a piston which pushes this redstone block, and it's like and then the redstone block just stays there. You know what I mean? So essentially, off of this pulse input of like this observer sees, oh, it's not a pulse input, it stays on, but whatever. It's essentially taking this and moving it forwards a little bit so that it doesn't get connected here. And actually, why am I doing that? Wait, I just realized I could have just blocked it off like this, no? Whatever. pretend like you did. See that? Pretend this is the only way is possible. Okay. That's just me being stupid. Oh my god. Whatever. That's why I have it like that. What? Oh my god, I think I'm losing my mind. Oh my god. Dude, this cabling, this redstone cabling is actually top 5 worst experiences of my life. Bro, I'm deadass hallucinating. My eyes hurt so bad. My fingers have carpal tunnel, bro. Like, why? This shit is so hard, bro. It's so tedious. But everything's done now. Everything's done. So ideally, this should work. So let's test this out. Alright, so let's do that example we had before. So that was 89 plus 59, or 8 and 16. That's 24, and then there's 1 left over. So there. So that's 89. We're not gonna look at the output yet. And over here, I want to make 59. The 1 and 2. Okay, so I got 89 plus 59. 89 plus 59 should be 148. And hopefully our answer will reflect that. So let's see. So that's our answer over there, okay? So let's figure out what this number is. So we got 1s, 2s, 4s, 8s, 16, 32, 64, 128. So we got 128 there. 64, 32, 16. 128 plus 16, which is what? 138, 144? 144 plus 1, 2, 4 plus 4. 144 plus 4 is 148. And that is our answer. 148. We did it. It works. We just added 89 and 59 in Minecraft using this thing that we just made. We actually did it. That's fucking sick, man. That is so sick, dude. That is so sick. Oh, man. I did it. I made something capable of doing 8-bit addition in Minecraft. But at the start of this video, I told you that our machine would be able to do subtraction as well. Do not fret, as this is actually really simple to do. We just have to figure out a way to represent negative numbers. Like, subtraction isn't really a real thing. Subtraction is just addition between negative numbers. Like, for example, 10 minus 5 is really just 10 plus negative 5, and our answer is the same. We're going to use something called 2's complement. It's a standard for binary numbers which allows them to represent negative numbers as well. See, so far we've been using unsigned integers, which just means we've been counting up in binary like usual. But unlike the numbers we usually use, where we can just put a minus sign before them to indicate that they're negative, a computer can't exactly recognize anything other than ones and zeros. So we need to figure out a way to represent negative numbers with only bits. 2's complement does exactly this. Basically, you take your binary number and you inverse all of the bits, so the zeros become ones and the ones become zeros. Then you add 1 to that number, and then you have your 2's complement negative number. Oh yeah, a neat way to tell if a 2's complement number is negative or positive is by looking at the leftmost bit, and if it's a 1, then the number is negative, and if it's a 0, then it's positive. Anyways, with 8 bits, without using 2's complement, and like unsigned integers, we can make any number from 0 to 255. But now that we're introducing negative numbers, our range becomes negative 128 all the way to 127. How about let's do this. How about we do 10 minus 5, right? So how do we make 10? Well, we can get a 2, 4, 8. We can get an 8 and a 2. So that's 10 right here. And let's say we want to subtract 5, right? So first let's make 5. So 5 would look like 4 and 1. So that's 5. But let's turn this into its 2's complement version. So we're going to invert all of the bits. So zeros become 1, ones become 0, and then we're going to add 1 onto it. So now this is negative 5. And our answer should just be 5, which it is. Good. Now let's do 5 minus 10. So let's have 5 here. And then let's have 8 over here. Let's convert this into 2's complement. So let's invert all the bits. Alright, and now let's add 1 onto this. So 1 plus 1 gives us 0 with a carry bit here. 1 plus 0 is 1. Okay, so that's 5 over there. This is minus 10. And we end up with, yeah, that's negative 5 in 2's complement. Cool. Our machine is capable of doing addition and subtraction with 8-bit numbers. Cool. That was actually a lot easier than I thought it would be, especially the actual gates. Like, the only hard part, I guess, was like trying to remember how certain logical simplifications work. Like, I low-key took me a while to remember the XOR identity, but I mean, I realized that I felt like I remembered an XOR being a part of the adder, so that's the reason why I remembered it. But that's the only part. Like when I had the pen and paper, it was a little bit tricky because I was just trying to remember how all this stuff worked. But other than that, like actually building the logical expressions in Minecraft, not too hard at all, honestly. It was pretty fun, honestly. And actually, even the pen and paper part, like even that was quite fun, because it felt like I was back in uni, or back in first year uni. And I haven't done that stuff in a long time, so yeah, this is pretty sick. I like this. Let's do another one for fun. How about let's do 67 plus 67. How about that? That's your little reward, guys. You brain-rotted motherfuckers. This is your reward. Let's do 67 plus 67. Boom, boom. 67 plus 67. We should get 134. Let's see. 128 plus 4, so 132 plus 2, 134. Yay! 6, 7. Okay, this is not going in the fucking video. This is definitely not making the cut, bro. Why am I just wasting my time? I need to take a break. All right. Well, that was my computer so far. And next episode, I'm gonna make some memory or some registers, pseudo memory, and we're gonna use that to do multiplication and division using our ALU. And then we'll also add some functionality. Like I do want an AND operand and an OR operation that's within the ALU, so it can't just be the addition and subtraction side of things, or like just the arithmetic side of things. But we do want to have some logical operations in the ALU as well, because that'll come in handy later on for certain more high level, like more like assembly level stuff, like when we actually make a we're gonna have to make some sort of like programming language or some sort of assembly for this, which I have no idea how I'm gonna do that, to be honest. I'll be completely honest, I have no idea how I'm gonna write, like, not write assembly. Like, I know how to write code in assembly, but I don't know how I'm gonna I don't know how I'm gonna create an assembly language in Minecraft. I have no clue. That's actually kind of put me in a bind. I can't lie. Now I'm kind of worried. If you enjoyed, make sure to subscribe, like the video, and yeah, this has been me, a complete redstone noob, made a computer in Minecraft. All right, goodbye.